this Chinese saying basically tells that the wise enjoys water, and merciful people or the benevolent enjoy the mountains, and the wise are active, the benevolent are peaceful or static or placid, and the wise are happy, and the benevolent live long. So this I mentioned about this because static lives long. We will learn this later in our class. Exactly match our static variable. The static variable lives long. Okay, this is very interesting, I think. Okay, then we have a test before the class. We give 2 minutes. Question is, what is the correct description of this variable definition? So const is here, is integer pointer. So which one is correct? Is single choice. First one, A and the star A can't be modified. B, A cannot be modified, and the star A can be modified. C, A can be modified, and star A cannot be modified. D, A and star A can be modified. Oh, sorry. Okay, let's check the results. So you can see here, most people select the correct choice is B, okay? Because we const is here, so this pointer cannot be modified, but the object or the integer pointed to by the pointer can be modified, okay? So this is what we learned in last class, top level and low level const. Okay. A second one is similar. Again, 2 minutes. So what is the correct description? Still a single choice problem. So I think because previous one, we have already demonstrated the results. So for this one, I hope most of students can have a correct answer. So A is A and star A cannot be modified. B is A cannot be modified and star A can be modified. C is A can be modified and star A cannot be modified. D is both A and star A can be modified. Okay, time is up. Let's check the results. So most students select the correct answer, C, right, C. So here, A can be modified. The pointer A can be modified. That means A can point to other integers, right? And because this is constant, so this pointer A now points to this constant integer. So this star A is a constant integer, cannot be modified. Okay. Next one. Maybe give 2.5 minutes. 在某个类中存在一个成员函数 void sort。以下可以作为承载成员函数声明的是多线题。So there is a member function in the class void sort. Which of the following member functions cannot be declared as overloaded member function? First one is like this, is void sort. Second one, have a default argument. Third one, only single argument. First one, has a different type of the argument.
老师，为什么中文题目和英文题目不太一样？一个是可以，一个是不可以。
Sorry. Sorry. Very good question. Thank you. 谢谢. So this one should be can. This should be can. Okay. Can be overloaded. Sorry about that. Okay, then we give maybe 30 seconds more. This should be can be declared. Okay, can be declared. Yep, sorry.谢谢提醒。So if you are affected by this results, so please contact our TA. Okay. Sorry. Contact our TA if you are affected by this. If you are confused by this, to make the wrong answer, please contact our TA. Okay. Okay. Then let's check the results. So A and D are the correct answer. Here, B actually will get compiling error because this one is similar to this one, right? Because we cannot differentiate between this one and this one. So this will get error. And this one, this C, because return type cannot be used as to differentiate between overloaded functions. So return type is wrong. Okay, this one cannot. Okay, And this is our last class. Now we will learn something new. Okay. First is constant expression. So because
老
we
师，老师，
请讲。
老师，刚刚那个 B 不会报错，它跟那个 A，它跟那个上面那个不冲突的。
B 不会报错吗？
是的，我刚刚试了一下。
好的，谢谢。回来让 TA 我们再试一下，这个可能是之前那个 TA，伟清你在吗？伟清在吗？哦 ，OK，我们回来让伟清确定一下这个问题，确定一下问题，OK， 好，谢谢。Okay, let's continue our class. You'll learn something new. From last class, we learned constant. Now we learn something related to constant expression. So actually, this is also related to inline functions. So that's why we also put it here, because we are learning inline functions later. So a constant expression. A constant expression is an expression that can be evaluated at compile time. So actually, this is not a constant expression. So we cannot use constant, non-const values to define static arrays. So this is get error. And if we do define a constant integer, then this is constant expression. Now, because the at compile time, the variable is known. So the compiler can define a static array based on this constant expression. Okay, so this is basic idea of constant expression. And then we have this const XPR keyword. So const XPR keyword can be used for both functions and expressions. And basically, it suggests the compiler to compute constant value from the function at compile time. That means we want to get okay. Someone is doing something. Okay. 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 Sorry, I may not have much time to check the message, so we'll continue our class. Okay. So this const XPR suggests the compiler to compute the value from the function at compile time, and it can be used with constructors. This const XPR can be used with constructors to construct a constant object. And also these const XPR functions are implicitly set as inline function. Actually, we learned inline function before. We also mentioned about this in this class. And the constant XPR is a constant expression. So it requires, so first one is suggests. That means the function may not be able to compute a constant value. But this one, constant XPR expression, requires we get a constant value at compile time. Otherwise, there will be compiling errors. Okay, so best practice or our design principle is that similar to inline functions, constant XPR functions should be defined in the header file. Okay, so this is an example. We have a const XPR function like this. So that means the compiler is suggested to compute a constant value from here. Okay, then we have a constant value here, and then we can use the function compute a constant value. Then we can define a static array. So that's the usage. Okay, key idea. And then we can also use constant XPR to define use constant XPR to define a variable, and also like this, we can define a constant integer, and we have integer here. And then if we want to define a constant expression like this, it's fine because A and B are constant values, right? We can get a constant value here at compile time. However, here if we define this as constant expression, we cannot modify A. Also because C is not constant, so this one gets error because compiler cannot do that, cannot compute a value from C. Okay, so this is a basic idea of constant expression. Because we learned const, so we also want to mention something about this. Okay. Okay. Now we learn something related to inline function. So we have learned this before. We know that macros can be replaced by inline functions, right? Function like macros can be replaced by inline functions. So what is inline function? We already learned this. I think we don't need to mention too much about this. And this keyword, and this is the grammar. So the inline keyword should always go with the function body, right? Function body. So like this, when we define the function body, it's a function body, then we have the inline keyword here. Okay? And also inline keyword is only a suggestion to the compiler, which maybe we ignored. And also you are suggested and to put all the inline function definitions in the header files. Then inline member function, we also learned that, I think, by default, the member functions with function body defined in the class is inline function. And also, we should not try to inline every function. We should not try to inline every function because making big functions inline may degrade the efficiency. Our original idea is to use inline function to speed up, right? To improve the efficiency. However, if we make too much inline, we get to very large functions, right? Very large functions. Then these big functions degrade the efficiency. This is because modern processors, smaller code usually runs faster due to better use of the instruction cache. So this is from the Google coding style. So if for those who have read the Google coding style, I hope you have seen this. Okay. This is from Google coding style. Okay. And these are typical usage, typically for the setter and getter function. So we typically use inline functions. Okay. So this is a inline function. Actually, we have a very simple example. So you can see here, it's inline. Inline and the main. So actually, the example is very simple. We have two compute function, and in the function we just do very simple functions, just compute the sum, and then return the sum. So one is inline, we can see here, as suggested, we put inline functions in the header file. So this is header file inline.h. And we have another version of the function, which is not inline. So we have a declaration here in the header file, and then we define function body in main.cpp. So actually function body is the same function body, but one is inline, compute is inline, compute 2 is not inline. Okay. Then we have a timer. We use timer to compute the runtime, and then we have some for loops to check how much time it takes for inline. So this compute is inline, first one. So first use inline, we compute the runtime for this recursive or a loop call of this inline function. And then for the second one, we use general function, same number of loops, and compute the time. Okay, so this is very simple program. So you can, as already made, so you can run it. We can see here, first one use inline. Actually, runtime is not better, right? So this is interesting. What I want to say is that due to the system scheduling or system overhead, different runs of the program takes different time. Okay, so sometimes it's longer, sometimes it's shorter. Right? This is surprising, right? So actually, we hope using inline it should be better. However, not the case. Okay, so sometimes we get better runtime, sometimes not better. Okay, so and also for different runs of the program, we get different runtime. This is because the system, our operating system, is use round robin， 就是时间片轮转时间片轮转的一种操作系统的调度方式把这个程序呢来执行，所以呢它的运行时间呢并不是每次都一样，这与系统的负载还有它的调度都有关系。So in this case, so I want you to sometimes in our experiments we also students tend to report, for example, the best runtime from 10 runs. I hope you don't do that. I hope you to, for example, you run 10 times of the program and you get the average of the runtime. That should be better. Okay, so this is for inline. Sometimes it's not actually not so effective. If you have some more suggestions on this, if you know something more related to this, you can share with us. Currently, I don't have a very good answer for this. I think the just because the function call overhead is not so much, maybe. Okay, so this is inline function, and next is namespace. So namespace is actually the idea is very simple, easy to understand. It is a name wrapper. It's a name wrapper. Wraps the names. Name wrapper to enclose user-defined names in a distinct space, so that name collisions will be avoided. So, for example, there are 3 students. For example, there are 3 students working in a team for a project. Then their names may have conflicts. So if each student have his own or her own namespace, then this problem is avoided. Okay, and this is namespace. So namespace is this keyword using and namespace. So actually for this namespace wrapper or name wrapper, a class, struct, enum, and union also have a side effect of creating a new namespace, because variables in the class, the member variable, and these member variables, we do not need to worry about the name clearance with other variables, right? So this is also a namespace. Okay, and this is a very simple example how we use a namespace. You just define a namespace like this, then all these names will be wrapped into this space by you. Then there's no name clearing between this F and another F outside, for example. Okay, then there are two ways of referring to the namespace. One is using namespace, the other one is using the name with the namespace, the space name. Okay, and this is one example. This is a complete example of how we use a namespace. So here in the header file, actually this namespace can be used across many different files or multiple files. So this file is in this namespace, same namespace, and there's another file. And this one, this source file, also this namespace. This one also this namespace. So the namespace can be used across multiple files. So in these different header files and source files, we have defined classes and member functions, right? Member functions like this. And then to use this namespace, we just by this using, we can open this namespace, and then we can use all the names defined in the namespace. Okay. So this is a very simple idea about this namespace. So our design principle is that never open namespaces by using in header files. Never do that, because our original idea is to use a namespace to avoid name clearing, right? But if we open this namespace in the header file, then in all the source files, the names are open. Then the name clearing maybe happen, right? If we do that, okay? Then the suggestion is that we open the namespace. We open the namespace here in the source file. So this is CPP file. The CPP file, okay? Okay, then this is namespace. Any questions? You can send the bullet screen message, or you just open your microphone. Okay, I think this idea is simple. So, okay. Then we'll learn static. So we mentioned that static or placid lives long, right? Just like tortoise, right? So I think this is a Chinese saying, static or placid lives long. So similar idea in programming world. So static data or static variable also lives long. Static variable also lives long. So this static data or static variable lives throughout the life of the program. Longest one, right? Because when the program terminates, anything will be terminated, okay? Even the memory leaks will be terminated. 这一点大家要注意啊，就是说，比如说我这程序有一个内存泄露，那我的程序 终止了，内存泄露还有没有呢？这个问题大家要注意。程序终止了，这个程序带来的所有内存泄露全都没有了，全都收回了啊，这个要注意啊。之前我们没有讲啊，就这个是大家要注意的。Okay, so this static variable is allocated once at a fixed address in the specific static data area. And this is not stack nor heap. Okay. So another static area. Okay. Actually, in the storage of our memory, the memory is partitioned into different parts. For example, maybe this is static. For example, maybe not at this place exactly. This depends on different design of the compilers. And this is stack. This is stack. And this is heap. Typically, typical designs will make a heap grow in this direction and make stack grow in this direction. Okay. When the two parts of the memory meet together, then all the memory is used up. And that's actually rare cases because this is very large memory. Okay. So static is another place. Example usage of static data. Here is an example. So here is a function. So in this function, we can define a static variable. Actually, as a grammar, we can use this. And this also works. And then for each function call, we will plus this variable by 1. And also we print the number of times this function called. So this is a typical way of recording how many times a function is called. So this is how we test. So this is a key, right? So the static actually is we can regard it as a global variable, actually, because it lives very long. Even we get to the end of this scope, it will not be deleted. Okay. But difference between global variable is that for a global variable, I can see here, the static variables in the function is initialized at the first time of the function call. That means first time function call here, then this variable is initialized for the first time. But for global variables or global static variables, it will be initialized before entering the main function. This is the major difference. Okay, 5 minutes break. Okay, okay, we continue our class. So this is static. So static keyword. So we have actually static has internal linkage. Static variables and objects and the static general functions can be declared or defined. And they are local to the translation unit. Translation unit means .o or .o or .cpp. Right? This is translation unit. So can be defined either in header or source files. And there are some other internal linkage, const and inline functions are internal linkage. We have learned that before. Again, we have something related to extern. Actually, we learned this before. So extern typically declares some external linkage. That means visible to the linker everywhere, external to the translation unit. So this is on the contrary of static, right? This is internal linkage, and this is external linkage. This is how we use extern. So for example, in a.cpp, we define a variable. This is a global variable. And then in b.cpp, we use extern. Then in this way, we can use this global variable without the need for header file. Without header file, it still works. However, the header files can be are necessary for multiple products, multiple file products. For example, most classes are defined in the header file, and templates are also defined in the header file. Then the static members, there's something related to static members belong to the class. They're shared by objects of the same class. So we can define some static members of the class and can be accessed by either the class name or the object name. And this is a static member variable, the keyword. So the keyword, static keyword, should only exist in the header file, in the class. And this is a way, and this provides a way of defining static arrays. We will have an example in this later. And we can also define static member functions. So static member function, again, static keyword should only exist in the header file. In source file, we don't need this keyword. And the static member functions cannot access non-static member variables or member functions. Okay. And this is an example of static array. So we have the example here. So here, this is a header file. We define the static member variables. One is static, another one is static const. We can see here, for static const, we can give it a value here. And sorry. And then we can use enum. And then we can define the arrays. The array. First one is use size. This is static const variable. The second one and third one is enum variables. It works. Okay. And in the source file, we need to initialize the static variables. You can see here, static keyword is omitted. We should not provide static keyword here, otherwise compiling errors. This is also a static member function, foo. This is static, you can see here. And we also omit the static keyword, otherwise compiling errors. And then in main, you can use it like this, okay? So this is a example. And then there are more example. One more example. I leave this to you to read. So static members can be used to interaction between different objects. So between objects of the different classes, then we have this, actually we have access control, right? We have access control, this one. And we can control modification of member variables by keyword const. So we can provide some interface with constant member functions, right? So that we can control the access between different objects. Then between objects of the same class, for example, static member variables can be used for shared data, because all the objects of the same class share one copy of the static variable. So they can communicate with each other, right? Because they have a single copy of the static data in the class. So they can share the data there. Okay, so this is interaction between objects. Now we have a singleton design pattern. We will learn this later when we learn design patterns. And now there's something related to this static grammar. If we want to ensure that a class ensure only one instance for a class, that means for this class we cannot define two instances, only one. Okay, so this is how we design such a class. We have a static member with object E, and then we set the constructor as private, like this, so that we cannot define a new object. Okay, so in this way, by setting constructor as private, we cannot define, right, any more instance. However, we have a static instance here, because this is from the designer side, right? The designer is will call this constructor. We have learned that designer have free access to any members, right? So this private access of the constructor will not limit the designer. So the designer can still initialize this egg E. So this single instance is initialized. Then it guarantees that we have one instance, right? Okay, so this is a singleton design pattern. However, it does not work. We can still have one more or two more instances in this way. So we can define an instance, and then we, by assignment, we can give it. We can get the value. So we can define new instances. So how to avoid this, or what is this? Actually, this is copy constructor. So we'll learn this later. Okay. Then this is for this inline and also static. Now we'll learn reference. Okay. Then for reference, we have an example here. So our question is how to swap, right? How to swap the two variables. So this is a typical way of swapping between A and B. So maybe we want to use a function to do this, like this, swap. Now how to define this swap? Does this work or not? We can define swap like this. This is this arguments, and then we can swap. Can it really swap or not? Answer is no, right? We know that because this is pass by value. Pass by value means we are making a copy. When we call this function, we are making a copy from this A to this A. So a copy is made. So modifying this A does not affect this A. Okay, So that's passed by value because we are working on the copy. We are not working on the original version or original value. So that's because passed by value does not work. Then here's another solution. Use global variables. Then we can swap, right? Because there are these two variables, global variables, so we can directly work on the global variable. So this works. However, we should not define too many global variables in our designs. So this is also a design principle. In our projects, I hope we do not define so many global variables, because global variables takes memory, and also when we take much memory, the runtime may be degraded a little, maybe. Also, there increases the more chances or higher chances of name clearance. Then is there alternative solution? We can use pointer, right? Can use pointer like this. So this works. This works. But if we call this function in this way, for example, we can initialize like the 0 pointer, then we swap it. What will happen? It may crash the program, right? So by careless user of this function, we may crash the program. Okay. Then is there a better way? A better way is reference. Is reference. This is reference. It's very elegant, very easy to use. Okay. Then what is a reference? A reference can be regarded as an alias of a given object or variable. For example, we have an integer value, and then we define a reference in this way, using this AND operator. Then two variables points to the same memory, or points to the same variable or same memory. Then modifying either one will change this memory. Okay, so that's the alias. Similar to our nickname. Okay. Then in more detail, a reference, actually it is a const pointer. We can regard it as a const pointer that is automatically dereferenced. And it needs to be defined and initialized simultaneously at the same time. So this is define and initialize this way. Once defined, cannot change. So it is const pointer, cannot be changed. And actually, we cannot have now references. We can have now pointers, but we cannot have now references. Okay. Here are typical usage of reference. First one is modify or return the value of function arguments like this. We have already defined this. This is how to modify the past arguments, right? And number two is to carry return values of a function. So for example, like this, we can carry a return value in this way, right? So this way, we are passing this out, right? Passing the reference out. We are not making copy, so it has better efficiency. Our design principle is that never return a reference to local variable. For example, if we define some variable here, then we return it, that is bad design, because the local variables, after returning the function, the local variables here will be deleted. So the reference maybe get meaningless, right? So we should not do that. But in this example, we are passing the reference out. So it's not local, so it works. Then efficiency. Okay, for reference, we will mention about that. For reference, it's suggested to use const. How about efficiency of this? So we have a very large class, then we copy, actually pass that value to call the function. So apparently this will be very low because we are making copy of large objects, very large objects. So this has very bad efficiency. So our typical usage is to avoid making copies of function arguments or return values for better efficiency by this, by reference. We are not making copy, we are just pass the pointer or pass the reference into the function. So it has better efficiency. So this is the design principle. We name it least privilege principle, to award function enough access to accomplish the task, but no more. Award least access. So for example, in this example, if we do not need to modify A and B, then we should get it const, use const to award least access control. And this gives better safety, and also efficiency may be improved. Okay. Then the number 4 usage is range-based loop. So for example, we define an array, and then we use auto to enumerate all the values in the array or in the list. But if we want to modify the elements, we have to use reference. We use reference to modify the elements. Okay? And these are the typical usage of the reference. Actually, we introduced reference for object cloning. Actually, object cloning is the basic reason why reference is so important. Okay, besides the previous usage. Then here is an example. So what are the results? So we have a class A, and we swap the two objects of A. So we get A and B. First get the value of A is I, get I, and then we set A, set B. Our question is, this function works or not? Can this swap the two variables, the two objects, or not? Answer is no, because again, it is passed by value. Although it is object, but it is passed by value, so it cannot be modified. So we are working on a copy of the original object, so it does not work. Okay. So it is passed by value. We are making copies. So how is the copy made? Actually, there is a copy constructor called for this. Copy constructor is called here. Okay. So what is a copy constructor? A copy constructor is a special constructor for cloning a new object from an existing one. And both objects should be of the same class. So our question is, can we define an copy constructor in this way? So if we define a copy constructor in this way, for example, if we define a copy constructor in this way, we just copy everything from the existing object. It does not work. Does not work. First of all, if we call this function, A, for example. First, we are making a copy from A to the parameter of A. Maybe this A. We are making a copy here, right? From A to this argument A. So in this way, in this case, we will call the copy constructor, right? To copy. Now we will call this function, that's because this is a copy constructor. When we call this function, we are also passing this A to make a copy of obj, right? So we're also making a copy here. So we are making another call of the copy constructor. Then if we want to make another call of the copy constructor, again, we need to make another copy. And then we want to call another time, right? So this is recursive call of the copy constructor if we just pass the value. So there's no way to solve this in this way. Only solution is to use pointer. Right. When we define the copy constructor, we cannot copy. We just use reference. We just use pointer. Then in this way, we can avoid the copy made in this, right? So we can define the copy constructor. So this is the idea, okay? So this is the grammar. I suggest you to remember it. And this is how we define some copy constructors, okay? We can also use delegating constructor to define that. A copy constructor is called when new objects are being defined from an existing one. For example, here, I have a default constructor, called the copy constructor here. This also calls copy constructor, although it is assignment. However, because we are defining a new object, so a constructor will be called, and we are providing an existing object, so a copy constructor will be called. So be careful about this. Be careful about this. A copy constructor will also be called if we have some function parameter like this, and we have some return type like this. No, in this case, assignment will not be caught. Okay, assignment will not be caught. In this case, because we are defining a new object, the constructor will be caught. So the copy constructor will be caught. Okay, so this is what I want you to remember. So whenever a new object is being defined, its memory is being allocated, a constructor will be called. Okay, so this is the case. This is the case. It may be default constructor with parameters, a copy constructor, or a move constructor. So we will learn move constructor later. So here, because we have already provided one, so we will call the copy constructor in this case. It will not call the assignment. However, if you have defined B and you have defined D, and then you have B equal D, then this is assignment. This is assignment operator, okay? Because we are now defining new objects here, okay? Then if the designer does not define a copy constructor, the compiler will synthesize one. So the synthesized one use bit copy. This is error prone for classes with pointer members. Okay, this bit copy. Okay. What is bit copy? For example, the memory of an object may look like this. And then for each row, it may be 4 bytes, 32 bits. And then if we want to make a bit copy, We copy all the contents bit by bit. Like this, bit by bit. So this is bit copy. This is error prone for classes with pointer members. Okay. So our design principle is that if you really need a copy constructor, always define your own copy constructor instead of the synthesized one. Always define your own. Okay. Why? Here's an example. In this example, we will show you why the copy constructor, a synthesized by compiler, is error prone. Okay. Okay. Sorry. You can see here, sometimes we can see that because it's already opened, some file is already opened, we can see that there are some files like this, maybe due to crash of the editor or other reasons. So we can remove that. Okay. Oh. For bit copy, our example is like this. So we have an integer array, this pointer, and the size of the array. And then in the constructor, we knew the array, allocate memory, and set it at 0. And then in the destructor, we delete. Okay. Then in set, we set an element in the array to a value, and then print. So it's very actually it's very easy. And in the source file, we print. Nothing difficult, I think. And then we have a bit copy, define an object, and then we copy constructor call, right? We call the copy constructor to construct another object. Then we print, and then we set. Then let's check the results, okay? Let's already make. So you can see here, printed many strange things, right? We can see here, and here's some results. Actually, we only modified. Actually, we only modified B, right? We only modified B. However, when we print B and A, both of them are modified, right? And also there are some crash, double free of corruption. This is caused by double deletion of the pointer, because both objects A and B will be deleted at the end. So this destructor will be caught. Right? So this array or this pointer will be deleted twice. So try to understand this problem. And Actually, this is because the bit copy and the pointer member. I just mentioned that if we depend on the copy constructor generated by the compiler, there will be such kind of bugs. I hope you can figure out the bug of this example. Okay, due to time limit, we will not have time to explain in detail about this example, but I hope you can figure out the reason. The reason is by bit copy. Okay. Then due to time limit, I will not go further. Okay, let's continue our class now. So in last class, we learned reference and copy constructor. Now we continue to learn this part. So before this class, I want to mention something about in-class talk. So for each class, we typically allow a maximum of 3 students to give in-class talk. So currently, we only allow these volunteers to give in-class talks. But in later classes, we may randomly appoint someone to give in-class talk if there are no volunteers. Okay, so because of the in-class talk, our classes may not be able to finish each slide in time. So it may be split into different parts, such as this slide. Actually, in last class, we do not have time to finish all of them in time. However, we will try to finish this part of the slides as quickly as possible, so that we have more time to give in-class talk and have more time to discuss on the in-class talk, ask questions. Then that may be more interesting for our students to learn other knowledge related to this programming. Okay, so first we will learn these slides, and then we will have 3 students to give in-class talk today. Okay. So in last class, we learned the reference and copy constructor, and then we have this example. We know that this example has some bugs, right? We have run it in last class. So how to so the bug is so we know that the bug is it does not work, right? Does not sorry. So we know that the bug is that the program crashes, right? We know that the bug it crashes. So how to solve this problem? We know that it's because of the compiler-generated copy constructor, right? Because compiler-generated copy constructor is bit copy, right? Bit copy. Bit copy means, for example, if we here we define one object A, and then we define another object like this, then this one is copy constructor. So copy constructor is called here because an object is being constructed from an existing object. So this is compiler-generated constructor, compiler-generated copy constructor, because we did not define one, right? We only defined the constructor. So bit copy is used here. So then, for example, if we have this A object and then we have the B object, and we know that so in A object, and this is ARR, as ARR, and the size, So this one, we know that this pointer points to some array, right? We know that because the constructor will do that here, right? So if we do bit copy, then B this pointer will have the same value. That means B's pointer also points to this array, right? So if we are going out of scope at the end, then the two objects will be deleted. So first, B will be deleted, right? It's like the stack, right? Stack. First in, last out, right? So so this one, I think the B will be first deleted, and then A will be deleted, right? So when B is deleted, then we can see here the array will be deleted, right? This one, this is deleted once, right? And then when A is deleted, the array will be deleted another time, twice. So that's double free or double delete error. So this crashes the program, okay? So to solve this problem, we need to provide our own copy constructor, okay? So our design rule is that never depend on the compiler's copy constructor, especially when there are pointer members. So be careful when we have pointer members. So our design rule is that we suggest all of you to define your own copy constructor whenever you want to use a copy constructor. Define your own, okay? Then this is for construction and destruction in the function call. So first, this is passed by value. So a copy will be made here. Then a copy constructor is called. Then if we define some local objects here, then the default constructor will be called. Then if we return the local object, a copy constructor will be called to return from this. So the return object is copied. Then out of this scope, then the destructor will be called for this local object, and then destructor will be called for this copy of the parameter, right? Copy. Then after that, destructor will be called to the return object. Actually, the return object of a function is also called temporary objects, right? Temporary objects. We know that, okay? So this is typical way. Okay, this is a very good question. Actually, it depends on the compiler. In some compilers, it may be optimized out. Okay, maybe the constructor for the return object, this one may not be called. For different compilers behave different, right? Different compiler is different. Okay, so typically it may be a copy constructor called. However, it may be optimized. Okay, for different compilers, we may not have that. So I suggest you to play with your compiler. Play with your compiler. You can input this program. You have this program. We have you can open the file to write down the debugging information, and then you have this how many class, and then you can use static to count, right? Count the number of objects created using this class. Okay, then you have in the constructor you plus the number, and in destructor you minus number by 1, and then in the copy constructor you also plus 1, right? Then you can monitor when you have the function call here. You have the function call here. You can monitor when is the constructor called and when is the destructor called. You can analyze. Okay, depend on our previous analysis, but I just mentioned that sometimes compiler behave differently, and it may be optimized. Okay, so there may not be such a for example, such a copy constructor called for the return object. Okay, so this is for you to do some exercise. You can copy the program into your compiler, into your editor, and then compile it and run it. Then you can get the results, and then try to understand when is the constructor called and why is copy constructor called here, right? Why is copy constructor called? Because a new object is being defined, right? So things like that. Try to understand what it behaves, why it behaves like that, okay? Then this is left for you to exercise, okay? Then after we have learned copy constructor, we want to learn how to avoid copy constructor, because copy constructor is not needed in many applications. So how to avoid copy constructor? How to avoid that? So a typical way is pass and return objects by reference or by pointer, right? By pointer, because reference is also const pointer, right? So it's also pointer. So by passing by reference, we can avoid the copy of the objects. So we can avoid the calling of the copy constructor. Okay. So for better safety, if we do not need to modify the content of the object, we can give a const here, right? Okay. Then that is the way to avoid the calling of the copy constructor. Then how to disable copy constructor? That means we want the copy constructor never be called. If they are called by mistake, then there will be companion errors. How to do that? The way to do that is just very simple. We can just declare the copy constructor as private in your class definition. Okay, then even the function body is not needed in this case. Then companion errors will occur when the copy constructor is called. For example, you may call a function like that, then this function is defined like this, then there will be companion error. Okay. There's another keyword delete that can help us to avoid the copy constructor or disable the copy constructor. It's like this. Delete can also be used to disable other member functions. Okay, so in this way, we just we don't need to write the function body. Okay, we just use similar to default, right? Similar to default, we just have an equal sign, then we have delete. It's fine. In this way, we can disable many different functions. So this is also assignment operator. We'll learn it later. Then in this way, we can disable certain functions. How can actually this is we call it conversion disabled. Actually, it's also constructor, right? It's also a constructor. But if we, for example, if we have a function which takes an object of type A, then if we call it in a floating point, then in this way, this conversion will be made, right? From converting from a float into an object, right? If we disable this, then this will get companion error. Okay, so this is conversion disabled. Okay, for assignment, we will learn it later. Okay, so for our previous example, for the singleton design pattern, we just mentioned that without disabling the copy constructor, we can still have multiple instances of this class egg. However, because we disable this here, now we can only have a single instance, okay? A single instance of this class egg, because we cannot call the copy constructor now, okay? Related to the copy constructor, I think most of you have used OF stream, right? Because in our homework, we also have this OF stream. Suggest you to learn it. And also, I think in our last semester in our department, our students also used this IF stream and OF stream, right? So I'm not sure if some of you have tried this kind of function that takes an object of OF stream. Actually, this does not compile, because copy constructor for OF stream class, this standard, this class in the standard library is disabled. Okay, and just using similar ways of our previous mentioned methods, declare it as private or deleted. So copy constructor is disabled. Actually, we will learn inheritance later. The base class of this OF stream is disabled, then all the classes are disabled in this inheritance the family. Okay, all the classes. And OF stream is a subclass of O stream, so it's also disabled. The copy constructor is disabled. Okay, so in this case, we can only use pointers, references, or pointers to pass an OF stream object. So this works. Okay. Now we learn something related to Mu constructor. So before learning Mu constructor, we need to learn L value and R value. So L value is the left-hand value that can be used to the left of this assignment operator. So its memory supports read and write. You can both read it or write it. Actually, most variables we use are L values. For example, if we define these two variables, then this one and this one are L values. So we can do some assignment like this. Also, a function call that returns a reference is an L value. So we can do this. If this function call returns a reference, then we can call another function like this. If this one returns a reference, this works. Okay, then this is L value. The R value is right-hand value of this assignment operator. So its memory is read-only. We cannot modify it. These R values include literals, such as integers, and this one hello world string. Right? Also temporaries returned from functions. So if we define this pointer and the integer, then this we get the address and this plus. So this is prefix plus, and this is suffix plus. And this one, these two are R values. We cannot modify it. We can only read it. We can only read the address of this. This is pointer P. Okay, and also if we return, it's not a reference. We return a value, a passive value return. Then this function call is the R value. We cannot modify it. Okay, this is R value and L value. Typically we cannot get an address of an R value because it is read only. We cannot modify it. If we can get address of it, then we can modify it, right? So these are the examples. We cannot get this. This is R value, so we cannot get address of it. And it works. Plus plus I equals 10. It works. It just for example, if I is 1, it's 101 before, and then after that, first it will plus 1. This is 102, and then I will be assigned to 10. So finally, I is 10. Okay, then you can have a test on that, I think. Okay, then we cannot get address of R values like this because this gets errors. However, we can get address of L value. Okay. Then related to this L value and R value is reference. The non-const reference only binds to L value. This is non-const reference, they only bind to L value. This is an L value. And this is R value, no, this gets error. This is R value because we return a temporary, so we cannot get address, so we can not bind it. So non-const reference cannot bind to can only bind to L value, cannot bind to R value. Then const reference binds to both L value and R value. So like this, const reference binds to both L value and R value, like this. Because we cannot modify it. Because R value cannot be modified. We just learned that, right? So it cannot modify it. We cannot, because it's const reference, we cannot modify it, so it can be bind to this R value. Okay. Then we can see here non-constant reference bind to L value. Constant reference binds to both L value and R value. How to bind only to R value? How to bind only to R value? This is R value reference. We have learned this, right? This is R value reference. R value reference only binds to an R value, which is going to be destroyed later, right? Destroyed later. So R value reference ensures safe access to the value of the temporary before it is destroyed. Okay, and this is R value reference, how to use it, right? It is usage. For example, we have the L value, and then we have the R value, and then we can get the R value reference, right? Like this. So this is R value, and then this gets error because this is L value, get error. And this is R value, and this is R value, it's fine, okay? So this is R value reference. Using the R value reference, we can define Mu constructor later, okay? So why Mu constructor is necessary? Here is an example. If we want to swap between the two objects, typically we do this. We must first make a copy and then assign B to A and then assign temp to B. Then during each operation, we have two copies of the different objects. So if the object is very large, then the copy is very expensive. It's very expensive. So actually, we do not need to make copies. We can see here, we just need to move the contents of object, right? We do not need to make copies, actually. So because anyway, we want to swap between them. We want to move the contents of A into B and move the content of B into A. So we want to move, right? We do not need to make copies. So with this in mind, we need to use Mu constructor, okay? So Mu constructor is a replacement of copy constructor when the source object will be deleted immediately after the copy operation. This means when we move it, the original source object will be destroyed because its content is already moved, right? So this is grammar. We use this R value reference, and the object should not be const because we need to move the content of it, right? Should not be const. It should be non-const. And to invoke this Mu constructor, we need to use the standard Mu function. Okay. So here, this Mu function means you can treat the argument X as an R value. That means it may be destroyed. Right? May be destroyed. You can destroy it in this Mu process. Okay. So if a copy constructor, this grammar, if a copy constructor or a destructor is defined, the compiler will not synthesize the Mu constructor, okay? So in this case, we have to define the Mu constructor by ourselves. So in our previous example, we just mentioned that because of double delete of the pointer member, there is a runtime error. And then we can do it. We can avoid the problem by defining a copy constructor, also a Mu constructor, right? Like this. So this is how we define the Mu constructor, R value reference, and then we can move the pointer, right? Move the pointer, and then reset the source, this pointer to 0, reset to 0. So in this case, we have moved the content of this object A. The array is moved to, actually, if we do this, the array in A will be moved to B, right? Will be moved to B. So in this case, A actually is cleared, right? Because its pointer is 0, right? It's 0. Now I have fixed this problem. Okay, now I have fixed this problem. Okay. Then back to our previous example, we can, if we do swap, we can do this. We can move from A to temp. Right? Move from A to temp. This invalidates A because we have used move constructor. Right? Then we can move from B to A and move from temp to B. However, because we are not defining new objects, we are not calling constructors here, right? So this is assignment operator. Assignment operator. So this is move assignment, and this is move assignment. Move assignment also needs this arbitrary reference. So we will learn this later when we learn the operator overloading. Okay. And again, this move assignment saves the time and saves the memory. Okay. We do not need to make copies. And especially the time is saved, right? Because we do not need to copy one from another the elements. We just move the pointer directly. So it saves runtime, okay? Let's check. Okay, so I have a question here. We define a very strange structure. We can also use class here. Class here. Okay, then we have some, actually, we define a struct inside another struct like this. And then we define, using this struct or class, we can define some objects and some objects and like this, right? So our question is, can this compile or not? The answer is yes. So this is actually called nested structure. So we can define some structure within another structure, right? If we are sure that this structure, for example, type 2, will only be used in type 1. It will not be used anywhere else, okay? So in this case, we can define nested structures, and we can use these nested structures within this type 1 to define some internal or member variables or member objects. So this is actually a special case of composition. Okay, we'll learn this later. So this is, and let's check the example in so the move constructor. Okay, then in the move constructor here, we can see we have defined the copy constructor and the move constructor and delete like that. And then in the source file, we just print. And then in main, we call this move, right? Call this move. So it's very actually it should work. So answer is correct now, and there's no bugs, no crashes, right? Okay. So this is what's left in our last class. I don't think so. You can have a try. I don't think you can define this type 2 object with outside this because this is nested in this structure. I don't think you can define such an object with outside it. You can check some grammar. Someone can answer this question. You can use blitzscreen message. I'm not sure this works or not. For example, type 1, 2, then you can define some objects, right? So this works. This works. Okay, then great. Then you can define it in this way, scope operator, because this type 1 actually acts as a namespace, right? Namespace. So you cannot directly use type 2, but you can use scope operator like the space, right? Okay, good. Okay, then this is what's left in the last class. Now we learn something new.